Hi, in this video we will simulate the startup circuit for the bandgap reference. When we designed the startup circuit, we said that it is hard to detect the necessity of the startup circuit in the simulations because most of the simulator will avoid the zero current state, and when we simulate everything will be fine, but it doesn't guarantee that when we do the IC in silicon it will work. So even though if we cannot see the necessity of the startup circuit in the simulation, we should design a startup circuit for every self-biased circuit. So this is our bandgap reference that we designed earlier. So let us simulate it once again. First let us do the DC simulation and sweeping the temperature from -40 to say 125 degree, and we need to plot the output, the reference voltage, and let us simulate the circuit. We got the reference voltage near to 1.2 volt, and this is without any startup circuit. So in the DC simulation we said the simulator will not show the necessity of the startup circuit. It will automatically avoid the zero current state. So to see the necessity of to see the significance of the startup circuit, we said we will do the transient analysis. So there is a chance for us to see the issue of startup in the transient analysis. So I am giving a transient of 500 microsecond. I am disabling the DC, and instead of giving a DC value, I am giving a pulse signal here. That means initially it will be 0. That means there is no supply. Then we turn on the supply after a particular time interval, and in that case we can expect that we will see the startup issue. So instead of VDC, I am giving V pulse here, and initially I want the voltage to be 0, and after some time I want it to be the VDD, and period I am giving a huge time period. Delay I am giving 100 microsecond delay, and I am giving 100 microsecond rise time also. Fall time and pulse width doesn't matter, and I am giving 0.5 second as the pulse width. Before plotting the reference voltage, let us plot the VDD first. So then you can understand why we give this much this kind of a pulse wave here. So we need to plot the VDD. So let us run the simulation. So this is what we wanted. Initially the VDD is 0. That means the IC is turned off, and now we applied the supply to the IC so that the supply voltage went to 3.3 volt. So this is the transient case. This will happen in reality when you make an IC, and if you want to test the IC, first initially the supply will be 0 and you will turn on the supply, and this will happen in reality. Okay, so now if you plot the reference voltage, you can see the issue of we can see the issue of transient. There is no guarantee that the simulator will show the issue. I am repeating that even though the simulator is starting now, it doesn't mean that it will work properly in silicon. So let us plot the reference voltage, and you can see the reference voltage is not coming to 1.2 volt. That is, the startup issue is here. Startup issue is present here. That means you can see the reference voltage is coming only to 300 or 350 millivolt. So it is not going to 1.2 volt. So we said what is the reason? We said the reason for this is this node will be near to 0, that is less than threshold voltage, and this node will be near to VDD, and there will not be a VTH difference in between the VDD and this node. So the current flowing through these two through this MOSFET will be very small current, that means only negligible current, leakage current will be flowing, so the circuit will not function properly. So let us analyze the current and the voltages also. So I want to plot the voltage here. We said it will be very near to VDD, so we'll plot both VDD and this node voltage. So you can see it is not exactly VDD but little bit less than VDD, but not the difference between VDD and this is near to 0.25 or 0.3 volt. Of course this is less than the threshold voltage, so only a negligible value, only a small amount of current will be flowing. So now we can plot the gate of the NMOSes also. So it is also very near to ground, that is 250 millivolt only. It is also below threshold value, so a subthreshold current, only a small value of current will be flowing. So these MOSFETs are not in saturation now. As a result, the current flowing through is very small. We can plot the current also. For that we have to select this current through the 3 branches and let us plot them. So you can see the current through the branches is in picoamperes only. It is not even coming to nano ampere, or we really designed it for 1 or 2 microampere, but now it is coming only the picoampere range. So you can see the current is 1.14 picoampere only. So in the transient analysis we showed that the circuit will not function properly without a startup circuit. So now we have to design a startup circuit for this circuit. So as we discussed in the theory session, we can design a startup circuit very quickly. We need an NMOS here. I am just copying the NMOS from here. So again, the size of this NMOS, how much it should be, it is not a big design issue. This because the startup circuit will function only for a small amount of time, so the size of this MOSFET is not very significant. So you need not give a big MOSFET here, and you don't need a matching on or those things, so you can reduce the size of the MOSFET. So I am giving a very small MOSFET here, and we said we will connect this MOSFET to the gate of the PMOSes, so that it will pull down the gate of the PMOSes to ground. It will try to pull down the voltage to ground, and the gate of this NMOS, we want to control this using another NMOS. And the gate of this NMOS is connected to this node. And we need a high resistance. I'm just copying this resistor here. So this resistance value is too huge. We don't need this much huge resistance here. So let us try with 10 kilo ohm of resistor, and let us check whether it will work properly or not. We need to save all the current. So output to be saved, select on schematic. So we designed the startup circuit, and we said we need a big resistor over here and big MOSFET here, big NMOS. So I'm making this little bit big, and let us run the simulation. And we are plotting the reference voltage. Now you can see the reference voltage came to 1.2 volt. So there is no startup issue now. The startup issue is solved, and we disturbed initially the circuit struck at zero current operating point. Now we disturb the zero current operating point with the help of the startup circuit, and now we want to analyze the startup circuit, how much current is flowing, how much voltage is appearing in the nodes of the startup circuit. So first of all, we plot the current through this MOSFET. So we want the current through this MOSFET to be zero when the circuit is functioning in the normal region. So you can see the current is almost zero, that is current is in 8 picoampere only. If in the normal region, you cannot see that in the normal region it is only 8 picoampere. So only in this time some amount of current is flowing. Only during this time some amount of current is flowing to the circuit. So this is the time where the startup circuit is working. So startup circuit will pump some current to the BGR, and once the BGR is working properly, then the startup circuit is turned off, and it is completely isolated from the bandgap reference. So you can see the voltage of the gate voltage of this NMOS. So initially it was some voltage before the BGR is working properly, and once the startup is done and the bandgap reference is working normal, then this node potential is pulled down, this gate voltage is pulled down by this MOSFET and below VT, so it is near to 150 millivolt only. So the MOSFET is turned off. So this is the first topology that we discussed for the startup circuit. Now let us analyze other topologies. So this is another topology of the bandgap reference that we discussed, and here also we can plot the DC analysis. So we are doing the DC, the temperature sweep we are doing from -40 to let's say 125, and we want to plot the output. So here this is the reference voltage. So let us run the simulation, and we got the reference voltage near to 1.2 volt, and I'm not doing the fine tuning. We already simulated the bandgap reference. What we are interested is in the startup circuit. So as we did earlier, let us make this to a pulse. So instead of a supply voltage as a DC, we are giving a pulse here, and initially we want the signal to be 0 volt, and after that we need the supply voltage to reach to 3.3 volt. 1 second time period, and delay I'm giving again 100 microsecond, rise time also I'm giving 100 microsecond, and the pulse width 0.5. So by giving this we made our VDD as in the real case. So let us plot the VDD. We plotted, select on schematic. This is the VDD we need. So in the transient response, the VDD will look like let us make the analysis to transient and give this 500 microsecond, disable the DC, run the simulation. So this is how the VDD supply voltage will look like. This is what we wanted. Initially we need the voltage to be 0, then when we turn on the IC, the supply voltage will reach to 3.3 volt. Now we want to see how the reference voltage is behaving. So let us run the simulation for reference voltage. So there is no reference voltage coming. It's again the issue of startup. We said when it could be when the op-amp output voltage is 0 volt, and these two nodes will also be 0. So it is stuck at 0 current state. and we need to design a startup circuit here. For that we said we need to forcefully pull up this node to some high value, so that the op-amp will try to make this node also equal to this by pumping some current to the output. So we need to pull up this node using a PMOS. So I'm using a PMOS for that. We need a small PMOS only. So one end of the PMOS we want to connect here, and other part to the VDD. Sorry, not here. We want to connect this to VDD, and we need an NMOS. We need a big NMOS here. To turn off the startup circuit once the bandgap reference is working properly. So we connect this gate to here, and we said we need a current mirror here. I copied the same MOSFET. So this is exactly the same circuit that we discussed in the theory session. So this current mirror is made, and we need a resistor here, and the resistor is grounded. So let us run the simulation again. We done with the startup circuit, so let us run the simulation. Now you can see the reference voltage is near to 1.2 volt. So before we designed the startup circuit, the circuit was not reaching to 1.1 volt, 1.2 volt. It was 0 volt in the output of the op amp. Now we got the reference voltage as 1.2 volt. This is a startup transient. You can ignore that, and the circuit will finally settle to 1.2 volt. And let us analyze the startup circuit. As we expect, initially this node potential will be below VDD, and once the startup circuit once the BGR started to function properly, this node potential should go to near to VDD. So you can see initially it was 0. So after the startup, after the BGR working properly, this is near to VDD, and there will not be any current flowing through this startup circuit. So we have one more topology remaining in the bandgap reference. That is this topology. So I'm saving the state so that we can use this again. And we have to simulate this circuit first. So first I want to simulate this for DC. So the DC value we are giving 3.3 volt. Let's start the ADE, and now I am loading the state that we previously saved. So this is the state that we saved. So first I am doing the DC analysis. So output to be plotted is the reference voltage here. So let us run the simulation. So it is working fine for the DC analysis. You can see the bell shaped reference curve here, and let us change the voltage source to pulse. So it is V pulse. Initially it should be 0. Again, then we need 3.3 volt. Period 1 second I am giving. Delay time 100 microsecond. Rise time also 100 microsecond, and the pulse width 0.8 or any value. So first of all, let's run the simulation to check the VDD. And VDD is coming as we expected. And now let us check what about the reference voltage. So we need to plot the reference voltage. Output to be plotted. We need the reference voltage. So run the simulation again. We don't want to plot the VDD now. We are just interested in the reference voltage. Here you can see the reference voltage is coming to 1.2 volt without any startup circuit. So this is one typical case where even though without the startup circuit, the simulator is showing that the circuit is working properly, but it doesn't guarantee that if we simply make the circuit on the silicon and we turn on the power supply, the circuit will work. There is no guarantee for that. So even though the simulator is not showing the issue of startup, we should design a startup circuit for the circuit, because this is a self-biased circuit. Even though the simulator, I repeat, even though the simulator is not showing issue of startup, we should design a startup circuit for this bandgap reference also. For this I am not designing it again, I am just copying from the previous design because the topology is very similar. So we can use the same startup circuit here also. Delete this part, and this to be connected here. This is exactly what we did here, and for the new topology also we can do the same. So this is the same startup circuit that we did earlier. So let us run the simulation again. Anyway, it will work without the startup also. Now also we got the reference voltage as near to 1.2 volt. So here with this video we are stopping the discussion on the bandgap reference. We discussed the different types of bandgap reference, and we simulated different types of bandgap reference. Then we designed the startup circuit for different type of bandgap reference. And keep in mind that even though the circuit work fine without startup circuit in simulation, it doesn't mean that it will work properly in silicon. We should design and add a startup circuit for every bandgap reference circuit. So we are stopping the discussion on bandgap reference here, and thank you for watching.